Okay, picture this. You're on the moon leading this mission, right? You're going to drill for water ice, but you're in one of those permanently shadowed craters, and all of a sudden sparks start flying. Like, not the good kind. This is triboelectric charging. You're just drilling, and it's making enough static electricity to fry your equipment.
Yeah, it can be a real problem.
Yeah, and it's not just a little zap. This is like hundreds of thousands, even millions of volts.
That's right, yeah.
So today's deep dive is exploring a potential solution for that.
Okay.
And we've got a research paper by S.K. Mishra and Trinesh Sana to kind of guide us through this.
That's good.
So what might seem like a minor nuisance here on Earth, a little static, that becomes a major problem on the moon, huh?
Yeah, absolutely. That kind of electrical discharge, I mean, you could jeopardize a whole lunar mission.
Yeah.
Especially if it damages, like, the sensitive electronics.
Right, exactly.
So, yeah, it's a big deal.
Okay, so let's break down, like, why this happens, first of all. So these permanently shadowed regions, they're not just dark, but they're bombarded with this diffuse solar wind plasma.
Right, yeah. So that creates this unique environment, and you get two distinct zones forming. And one of them is just packed with all these high-energy electrons.
And they call that region?
They call it the electron-rich region.
Makes sense.
Yeah, pretty straightforward.
Yeah.
And then at the edge of the crater, you get this kind of more balanced plasma region.
Okay.
Or what they call quasi-neutral.
Okay, so we've got this electrically charged environment, and then we introduce a drill.
Right.
What happens?
Well, when you rub a balloon on your hair and you get that static?
Yeah.
It's kind of like that, but on a much grander scale.
Okay.
So as this drill interacts with the lunar regolith, that's the moon's surface material.
Right.
It picks up a negative charge, and then the dust particles, they become positively charged.
So it's like we're making this giant static electricity generator.
Pretty much, yeah.
Right there on the surface of the moon.
Exactly. And because of that electron-rich environment, right? That negative charge on the drill, well, it can build up to these really dangerous levels.
Okay.
And that's where this new research comes in.
Okay.
So instead of trying to change the lunar environment, right?
Yeah.
They're saying, well, let's focus on the drill itself.
Okay. So how are they proposing to do that? I know it involves something called nanostructuring.
It does, yeah.
Which, honestly, I don't even really know what that means.
Okay, so it basically comes down to, like, manipulating materials at the nanoscale. We're talking incredibly tiny.
Okay.
And what they're suggesting is coating the drill's surface with these microscopic spikes. Almost like a bed of nails.
Okay.
But millions of times smaller.
Okay.
And these are what we call nanotips.
So we're fighting this massive static electricity with tiny spikes.
Right.
I'm a little skeptical.
Yeah, I can understand that.
How do these nanotips actually prevent that dangerous charge buildup?
So they act as what we call field emission centers.
Okay.
So they create these pathways for the electrons to kind of escape from the drill's surface. Like imagine little escape hatches for the built-up charge so it doesn't reach those like super high levels.
Okay, I like that image, but I'm still trying to figure out how can these tiny spikes actually make electrons escape?
Right?
It almost sounds like magic.
It might sound like magic, but it's actually physics. Okay. Quantum tunneling, to be precise.
Okay.
So imagine you're trying to roll a ball over a hill.
Okay.
Normally, you need enough energy to push it all the way up.
Otherwise, it just rolls back down.
Exactly.
Yeah.
But in the quantum world, sometimes that ball can just tunnel right through the hill, even if it doesn't have enough energy to go over.
Wow.
And the nanotips on the drill are creating that situation where the electrons can tunnel away from the surface.
Okay.
Even though they wouldn't normally have the energy to escape that negative charge buildup.
So the nanotips are like creating these shortcuts.
Yeah, you can think of it that way.
For the electrons, so they can bypass that energy barrier.
Exactly.
Okay, that's pretty mind-blowing.
It is pretty cool.
But does this actually work, though? Like, I mean, I'm hearing the theory.
Right.
But have they actually seen promising results?
Yeah, so in the research, they've done some pretty compelling calculations.
Okay.
And their models show that a surface with these nanotips can actually reduce the electrical potential on the drill to a safe level, like around 23 volts.
Wait, 23 volts?
Yeah.
That's a huge difference from the millions we were talking about.
Yeah, it's a massive reduction.
That's incredible.
Yeah, it really shows you the potential of this approach.
Wow.
And what's interesting is it's a passive solution. You don't need to add like a bulky power source or anything like that.
So just by changing the surface of the drill, at the nanoscale,
Right.
we can prevent this problem, this huge problem.
That's the idea, yeah.
It seems almost too good to be true.
Well, there's always practical considerations.
Yeah, I was going to say, it's rarely that simple.
Yeah.
What kind of hurdles might there be, like, if we were going to actually implement this on the moon?
Right. So manufacturing these nanostructured surfaces on a large scale, it's not easy.
Yeah.
It's tricky. Like, imagine trying to create this perfectly even bed of microscopic spikes on a drill bit,
Right.
It's delicate.
Right.
And we need to make sure it's reliable and
Yeah.
cost-effective if we actually want to use it for lunar missions.
Yeah, that makes sense. It's one thing to show it works in the lab,
Right.
but it's a whole other thing to actually produce it
Yeah,
on a scale large enough for space exploration.
exactly.
And I imagine durability would be a big concern too, right?
Oh, absolutely.
I mean, these nanotips, they're so small.
Yeah.
How do we know they're going to hold up? Like on the lunar surface,
Yeah, that's a crucial point. They need to be tough.
right?
They got to be resistant to wear and tear. I mean, they're going to be subjected to extreme temperatures.
Yeah.
Radiation, and that lunar dust is pretty abrasive.
Yeah, for sure.
So yeah, choosing the right materials and making sure the manufacturing process creates a really robust structure, that's going to be key.
Okay, so we got to make sure they can be made reliably
Right.
and that they're tough enough for the moon.
Yep.
Anything else we need to consider?
Well, contamination.
Oh, right.
We don't want those nanotips breaking off,
Yeah.
polluting the lunar environment or even worse, damaging sensitive equipment.
Oh, yeah. It would be kind of ironic if this solution to one problem
I know.
created
Exactly.
Yeah.
So researchers are looking into ways to make sure those nanotips are securely attached
Okay.
and that the materials are compatible with the lunar environment.
Right.
So there are definitely some hurdles, but the potential benefits, I think they outweigh the challenges.
Yeah, that's true with any new technology, I guess.
I think so.
There's always this period of refinement
Yeah.
before it becomes like widely adopted.
Yeah, absolutely. And that's where further research and development comes in.
Uh-huh.
We need to test it, evaluate it,
Yeah.
all sorts of environments,
Right.
just to be sure it's safe and effective for lunar applications.
Yeah, that makes sense.
But this is amazing technology, and, it's designed for the moon.
Right.
But it got us thinking, could we use this to combat static here on Earth?
As you were talking about all those potential issues, the contamination, the durability and all that, I was thinking the same thing. I mean, those wouldn't really be as much of an issue here, right?
No, not at all.
I mean, we've all experienced static.
Oh, yeah.
I mean, it's annoying.
It is. It's a pretty common phenomenon.
Yeah.
I mean, think about it. Getting zapped by a doorknob,
Yep.
clothes clinging together in the dryer,
Yep.
that annoying static when you brush your hair, it's all triboelectric charging.
And it's not just annoying, right? I mean, static discharge can damage electronics.
Exactly.
Yeah. Especially sensitive components. And that's where things get really interesting.
Okay.
So imagine smartphones, laptops,
Right.
virtually immune to static damage.
Huh.
That could mean they last longer, they're more reliable,
Yeah.
potentially even cheaper for consumers.
Okay, now I'm starting to see how this could be a big deal.
Yeah.
Are there other industries where we could apply this?
Oh, yeah, for sure. Think about manufacturing.
Okay.
Electrostatic discharge, it can cause huge problems.
Right, yeah.
Damages components during production,
Right.
leads to delays, financial losses.
Huh.
It's a big deal.
What about healthcare? I mean, isn't sterility a huge concern
Oh, definitely.
in hospitals and stuff? Could this help with that?
It could. If we could control the static buildup on medical equipment,
Yeah.
it could help ensure that it's safe and sterile, which is obviously crucial for patient care.
Right. Yeah.
And the applications, they go way beyond that. Transportation, energy.
Right, yeah.
I mean, static buildup, it can be a real safety hazard.
Especially when you're dealing with flammable materials.
Yeah, that's a good point.
So yeah, lots of potential there.
Wow, this could really have a huge impact across so many different sectors.
I think so, yeah.
It's a good reminder that sometimes the most groundbreaking innovations
Right.
come from these really niche areas of research.
Yeah, for sure.
Who would have thought that studying static electricity on a moon would help us solve problems here on Earth?
It's pretty amazing.
It really highlights the importance of scientific curiosity, huh?
Definitely. And the interconnectedness of different fields,
Yeah.
It's not all separate boxes. It all ties together.
And it reminds us that solutions for these seemingly complex problems
Right.
can be really elegant.
Sometimes, yeah. Sometimes the simplest solutions are the best.
Speaking of elegant solutions, I'm curious about those nanotips again.
Okay.
How do researchers actually control, how much charge is dissipated.
Okay, so
Can they fine-tune it?
they can, based on the application. Exactly.
Yeah.
It all comes down to the design of those nanotips.
Okay.
By adjusting the size, the shape, the spacing, they can control the strength of the electric field.
So it's like custom-designed escape routes.
Yeah, you could think of it that way.
For those electrons.
Yeah, like designing a microscopic valve that controls the flow of charge.
Wow, that level of control is really impressive.
It is.
It really opens up a lot of possibilities.
Yeah, for tailoring this technology to specific needs.
I'm really starting to see the potential here.
It's pretty remarkable. And we're just scratching the surface,
Yeah.
Nanotechnology.
Right.
It's a rapidly evolving field that could revolutionize so many aspects of our lives.
Yeah. Makes you wonder what other seemingly simple solutions are out there just waiting to be discovered.
I think there are lots.
Yeah, it really makes you think about all the things we kind of take for granted, like static. It's just this little annoyance.
Yeah.
But who knew that it could lead to these incredible technological advancements?
I know. It's pretty amazing. That's the beauty of science, right?
Yeah.
It often starts with just being curious about something that seems really mundane.
Yeah.
And then sometimes those investigations, well, they lead to these huge breakthroughs that have, like, far-reaching implications, and they impact fields that we never even anticipated.
Yeah, it's like this chain reaction of discovery where one little insight can just spark all these others.
Yeah, it's pretty cool.
And in this case, that initial spark might come from something as simple as drilling for water ice on the moon.
Exactly.
But speaking of those lunar ambitions, I'm curious, did the researchers in this paper, did they talk about like a timeline for when we could actually see this tech on a lunar mission?
That's a great question. And I'm sure a lot of space enthusiasts are wondering the same thing.
Yeah.
This particular paper focuses more on the like theoretical and computational aspects of this nanostructuring solution.
Right.
But the authors definitely seem optimistic about its future applications in lunar exploration.
Okay, so it sounds like we're still maybe a few years away from seeing these drills with nanotips on the moon.
Yeah, I'd say so.
But it is encouraging to know that people are taking this research seriously.
Oh, yeah, definitely.
And that it could lead to, safer and more efficient lunar missions.
Absolutely. And the possibilities, they go way beyond drilling, too.
Okay.
Like we've been talking about, this tech could be applied to rover wheels, spacesuits, basically any surface that could experience triboelectric charging on the moon.
Yeah, I mean, imagine a future where rovers can just, roam around without having to worry about static frying their electronics, or astronauts could explore with more confidence, knowing that their suits are protected.
It's an exciting vision, isn't it?
It is.
And it really shows you how transformative nanotechnology can be for space exploration.
Yeah.
But as we've also talked about, the implications of this research, they go way beyond the moon. They come back down here to Earth.
Right. And we've touched on some of those applications like electronics, manufacturing, healthcare.
Yeah.
But what other areas do you think could benefit from this?
Well, the possibilities are pretty much endless.
Okay.
Think about areas where static electricity is not just annoying, but actually dangerous.
Okay.
Like in aviation, static discharge, during fueling.
Oh, right.
That could be a real problem.
Yeah, I've seen those warnings at gas stations,
Yeah, exactly.
Turn off your engine, avoid static.
Right.
So if we could use nanostructuring to reduce those risks. Make it safer for everybody.
Exactly.
Yeah.
Or transporting flammable liquids,
Yeah.
I mean, even a small spark can be catastrophic.
Right.
Yeah.
It's incredible to think that something so tiny, like nanotips, could have such a big impact on safety.
I think so, yeah. It's pretty amazing.
And the applications go even further than that, right?
Right.
I mean, imagine putting this technology into fabrics.
Yeah.
Make clothes that are resistant to static cling.
Right.
Or use it on surfaces in clean rooms to prevent dust buildup.
Yeah. So safer airplanes, fuel tankers.
Yeah.
Static-free clothing, dust-repelling surfaces.
I mean, the possibilities really are endless.
I think so.
It's amazing.
It all comes back to thinking at the nanoscale.
Yeah. Well, this deep dive has definitely been an eye-opener.
It had.
Who knew that a problem as specific as triboelectric charging on the moon would lead to such a versatile and transformative technology?
It's been a really fascinating exploration, and
Yeah.
hope our listeners have enjoyed it as much as we have.
I agree. And to our listeners, we'd love to hear your thoughts.
Yeah.
What other applications can you imagine for this nanostructuring technology?
Right.
Head over to our website or social media, share your ideas.
Yeah.
We always love to hear from you.
We do.
Thanks for joining us on this deep dive.
Thanks, everyone.
We'll see you next time.